Hey everybody. All right, welcome back. We're moving on from our chapters about triangles. You just got done learning trigonometry, right? Triangle trigonometry. And we're going to start working in this chapter 8 with quadrilaterals. Now, for this first section in chapter 8, we're going to focus on more than just quadrilaterals, but that will be the focus of the chapter as a whole. In this video, we're going to be working with finding angle measures in polygons, as you see, and we're going to focus today on the interior angle measures in polygons. We'll have another video in which we're finding exterior angle measures in polygons. Now, one of the things that is a very simple task, but is very important, is when you're working with polygons, you got to know how many degrees, as they say, are in a specific shape. Now, that's different depending on how many sides the polygon has, and I want to take you through how that's determined. All right, and I'm going to start you off with the one that you know. You already know that a triangle has 180 degrees. All right, so 3 sides. For every one of these, I'm going to write down a value of n, and that value of n is going to represent the number of sides for the polygon. When n is equal to 3, the sum of the interior angle measures is 180 degrees. All right, now you may or may not know what the sum of the interior angle measures is in a quadrilateral, but let me tell you how you make that determination. What we do to figure out how many, or the easiest way, I suppose, to figure out how many degrees are in a certain shape is you figure out how many triangles can you make, non-overlapping triangles can you make, whose interior angle measures correspond with the interior angle measures for that shape. Now, that might sound confusing, but watch, in practice it's not that hard. What I'm going to do is I'm going to pick one vertex, it doesn't matter which vertex of this quadrilateral, and I'm going to draw every diagonal that I can from that vertex. Okay, so let's say I pick this point and I draw a diagonal right there. Now, I want to make sure that this vertex is connected to every other vertex in the quadrilateral. It was already connected to the bottom one and top one to begin with, and now it's connected to the only remaining one. And look at how many triangles then are formed when we do that. You can form 2 non-overlapping triangles by drawing diagonals within a quadrilateral. All right, so when n is equal to 3, when there's 4 sides, when n is equal to 4, you have 2 triangles, and that means you have 360 degrees. All right, and I'm going to keep doing the same thing going along the way. Now I've got a pentagon. I'm going to pick one vertex, any vertex. I'll just take the top one, and I'll connect it to every vertex it's not already connected to. And, well, that takes care of that. And then we'll see how many triangles that created. Obviously, you can see it's 3. But there are the 3 non-overlapping triangles. And since we're able to create 3 non-overlapping triangles, we would say that when n equals 5, you got 3 triangles, and there's 180 times 3, or 540 degrees. Kind of get the idea here? Okay, now there's a pattern that I want you to notice, and that pattern is going to be the relationship between the number of sides and how many triangles can be created. Now, when n was equal to 3, there is only 1 triangle. I'm not going to write that there, but you can see that. When n equals 4, you had 2 triangles. When n equals 5, you had 3 triangles. You'll probably have the correct pattern in mind. Let me show you one more just to illustrate that that pattern is correct. Here I've got, let's see, a heptagon, I believe. I've got 1, 2, 3, 4, 5, 6, 7 vertices. So yeah, 7 sides. I'll pick this vertex and connect it to every vertex it's not already connected with. All right, and you see here 1, 2, 3, 4, 5 triangles. Yeah, there were 7 sides, 5 triangles. Were created, and if you take 180 degrees and multiply it by 5, you're going to get 900 degrees. It means there's 900 degrees in a heptagon, a 7-sided polygon. All right, and so hopefully you noticed the pattern I was talking about. The number of triangles that you can create is always 2 less than how many sides the polygon has, isn't it? We got 2 triangles out of 4 sides. We got 3 triangles out of 5 sides. We got 5 triangles out of 7 sides. Well, here we've got 9 sides, I believe. I'm going to count the vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, we got 9 vertices, so n equals 9. And hopefully the obvious conjecture then is that there would be 7 triangles that you can create And indeed, I'll show those to you. There are 7. I'd have to, there's 2, 3, 4, 5, 6. Well, you got to count the regions afterwards, I suppose. 1, 2, 3, 4, 5, 6, 7 triangles. And then 7 times 180 is 1,260 degrees. So that's how you know what the sum of the interior angle measures is in a polygon. Well, let's extend that to an n-gon. And an n-gon, as you may recall from Chapter 1 when you learned to classify polygons, just means a polygon with n sides, where n can be any positive integer of at least 3. All right, you can't have a 2-sided polygon, for instance. Now, what we did was we took how many triangles you could make out of the polygon and multiplied it by 180, and we determined that the number of triangles that you can make was always 2 less than the number of sides. So the sum of the interior angle measures in an n-gon would be n minus 2, that's how many triangles there would be, times 180. That formula right there will tell you the sum of the interior angle measures in any convex polygon. Great. Well, let's do a couple of problems with that then. First, I want to see if we can find the sum of the measures of the interior angles of these convex polygons here, an octagon and then 27-gon. Again, from Chapter 1, we learned some polygons, the names of some polygons based on their sides. An octagon, of course, you hopefully remember, has 8 sides. So, the sum of the angles, interior angles, is going to equal then to 8 minus 2 times 180, and 6 times 180 is 1,080. All right, there's 1,080 degrees in an octagon. So you get the idea of what you do. Go ahead and do this for the 27 guide, please. All right, I'm just trying to copy this thing right here. All right, ignore that random G right there. It's gone. Okay, so sum of the interior angles would be 25 times 180. All right, 27 minus 2 times 180. And 25 times 180 is 4,500 degrees. Okay. And then you ought to be able to use the sum of the interior angle measures of a polygon in order to find missing angle measures within polygons. Got a couple polygons drawn here. You need to know how many sides are in each, and you need to know what the sum of the interior angles measures is in each. And once you do that, you're going to be able to make equations to solve for the value of x in each picture. Now the first one, you can count either the sides or the vertices. There are 5 of each here. You see me counting the vertices. There's 1, 2, 3, 4, 5. And so we need to know, first of all, what is the sum of those interior angles. And that's going to be found by multiplying 3 times 180, right? 5 minus 2 is 3. 3 times 180, 540 degrees. That's one you ought to have memorized, actually, eventually, is that there are 540 degrees in a pentagon. And then if we're saying the sum of the interior angles equals that, well, then we can make an equation where we add up the angle measures and set it equal to 540. Now, I could write x plus 75 plus 11 plus 90 equals 540, but I like to collect my like terms when I make the equation. All right, if we're going to add up all 5 of these angle measures, well, we're going to have an x plus x, so we're going to have a 2x. And then we can add up the constants as well. 90 plus 111 is 201. 201 plus 75 is 276. So there, we showed that the sum of the angle measures equals 540. Then we'll do a little bit of algebra to find the value of x. Let's see, 540 minus 276 is 264. And then divide by 2, we get 132. So those 2 missing angle measures there were each 132 degrees. All right, go ahead and try part B. You should pause the video and do this on your own. All right, first of all, you should have figured out that there are 360 degrees in a quadrilateral, and that is a quadrilateral right there. And then when you added up the common sides, well, the like terms, to add the angle measures together, you ended up with 5x plus 35 is equal to 360. Then 5x equals 325. So then x was equal to 65, which means you had a 65-degree angle right here. You had a 130-degree angle right there. You had a 135-degree angle right there. Those four angles would add up to 360. That's how you check your work, actually, is make sure they add up to 360, or 540 if it was a previous problem, you know? All right, great. Now, one more concept that I want to get into. You now know how to find the sum of the interior angle measures, but whenever you have a regular polygon, you ought to additionally be able to determine what is the measure of each interior angle. All right, now there's a quick, easy pattern that I'm going to show you here. And let's start with some regular polygons that you know. Recall that regular polygons, their angle measures and their side lengths are all equal to one another. All right, they're equilateral and equal angular. Well, in a regular triangle, you know that each angle is 60 degrees, but how do you determine that? Well, there's 180 degrees in a triangle, and you divide it by 3. That's where the 60 comes from. You know that a square is a regular quadrilateral, and you know that each angle in a square is 90 degrees, right? Well, that's because there's 360 degrees in a quadrilateral, and if you divide that by how many angle measures there are, then you get 90. All right, so if we apply that then to this pentagon here, we've got 5 congruent angle measures. We've already determined once or twice in this video that there's 540 degrees in a pentagon. So if all the angles are equal, they'd all be 540 divided by 5, and that's 108 degrees. All right, now to generalize, if you have an n-gon, a regular n-gon, meaning all the sides, all the angles are congruent for a polygon with n number of sides, the way you can determine what each interior angle measure is by first finding the sum of the angle measures. All right, you had to know how many degrees are in the shape, so that's your n minus 2 times 180. And then you divide by how many of those congruent angles there are. All right, so n minus 2 times 180 divided by n tells you the measure of each interior angle of a regular polygon. Let's use that formula to solve a couple problems. All right, right now what I'd like us to do is to find the measure of each interior angle of a regular decagon. Notice the word regular in the directions there, very important. Also, notice the word each. It's asking for each interior angle measure as opposed to the sum of the interior angle measures as we were asked for in the previous examples. All right, and so we're going to do this by n minus 2 times 180 divided by n. All right, a decagon has 10 sides, right? So n is 10. So you get 8 times 180 divided by 10, and that will give you 144 degrees. All right, so there's 1,440 degrees in a decagon. So in a regular decagon, each angle is 1/10 of that. All right, go ahead and figure out what the measure of each interior angle of a regular 100gon would be. So you're doing 100 minus 2 times 180. That's 98 times 180. That's 17,640 degrees. And we have 100 of those angles. So that's going to give you 176.4 degrees as the measure of each interior angle of a regular polygon. Now, good extension question to this is, what do you think the maximum measure of an interior angle for a regular polygon would be? Any ideas? Well, you can't have an angle that's more than a straight angle, can you? And you can't have a polygon if all you have are straight angles. So you're never going to have an interior angle measure that's greater than 180 degrees in a convex polygon. All right, one more question, which is going to use that same concept of how many degrees are in each angle of a regular polygon. Here I'm telling you that each interior angle of a regular n-gon is 156 degrees. Find the value of n. Now, here's essentially the question. Since I'm telling you you have an n-gon, and I'm telling you to find the value of n, what I'm asking you to do is figure out how many sides would a regular polygon have if each of its interior angle measures is 156 degrees. Okay, well, you know that the way you calculate each interior angle measure of a regular polygon is n minus 2 times 180 over n. So in this case, we're saying that that is equal to 156. And if we solve that equation, then that'll tell us how many sides this particular polygon would have to have. Well, let's get rid of the denominator here. Let's multiply both sides by n. And that'll give me 156n on the right side. It'll cancel out this n. I'd also like to go and use the distributive property on this step. Let's make this 180n minus 360 on the left. Subtract 156n from both sides and add 360 to both sides. And then 24 goes into 360 15 times. Now with a problem like this, if you didn't get a whole number value, the question isn't right, or you made a mistake, because you can't have 13.8 sides, for instance, can you? Well, there you go. So a 15-gon, a regular 15-gon, its angles would be 156 degrees each. Guys, that's the video. Thanks for watching. The next one will cover the exterior angles of a polygon. See you later.